After the introduction to nanotechnology, let's now look back to the history of nanomaterials and nanotechnology. Nanomaterials have existed in nature long before scientists could even imagine them. These materials exist in nature and were in use for centuries since ancient times. Chemists have dealt with naturally occurring nanoparticles all along. Think of molecules or viruses. They are of nano size. Toxicologists have dealt with nanoparticles that are the result of modern human life, such as carbon particles in exhaust of combustion engine. For example, tire manufacturers used nanoparticles, carbon black, to improve the performance of tires as early as in 1920s without being aware of it. In medieval time, artists used gold nanoparticles to achieve the bright red color in church windows. As atoms and molecules are nanoscale objects, we can even say that we are surrounded by and made of nanostructures. The existence and importance of nanomaterials could not be realized due to the lack of proper instruments and devices to deal, study, and handle the materials of such a small size. Coming to the history of nanomaterials, our planet is an important source of natural nanomaterials. Volcanoes, wildfires, dust storms, and sea spray are natural processes that create nanomaterials. Plants, insects, and even people also contain many nanostructures. For example, lotus flowers' leaves are self-cleaning and water repellent due to the nanostructures of their surface. Our bones are also composed of nanostructured materials. Even the most fundamental building block in our lives, our DNA, is a nanomaterial. Nanomaterials are also elsewhere in the universe, for example, in cosmic and moon dust, and have also been found in the meteorites that have landed on Earth. Nanomaterials were produced by humans in ancient civilizations. Many clay minerals contain natural nanomaterials and have been used for thousands of years, for example, in construction, medicine, and art. Here are examples of some handmade nanomaterials used in medieval times. Several historical artifacts owe their beauty to nanomaterials. We were unknowingly using amazing features of these since long time. The nanoscale is extremely small, and in earlier time, advanced microscope and equipments that can work at such an incredible small scale were not available. So mankind couldn't realize the science behind their interesting properties. The discovery of high-end experimental setups like scanning electron microscope or atomic force microscope has made it possible to work at the nanoscale. The concept of nanotechnology was introduced in the year 1959 by an American physicist and Nobel laureate Richard Feynman. When at the annual meeting of American Physical Society, he presented a lecture titled "There is a Plenty of Room at the Bottom." By bottom, he meant by the downsizing of the material. He suggested the possibility of manipulating of matter directly at an atomic level. The idea of physically working at the atomic level had never been thought of before. To promote this idea, Feynman threw two challenges to the scientific community. The first was to build a tiny but functioning electric motor which is only 1/64 cubic inches in size. The second was to miniaturize the page of a book to a scale of 1 upon 25,000, smaller, sufficient to fit the entire Encyclopedia Britannica on the head of a pin. His idea was to downsize the devices up to the atomic level, which is actually a nanoscale. He described a hypothetical vision of using machines to construct smaller machines and go down to the molecular level. In the drive for downsizing the technology suggested by Feynman, after 15 years, Norio Taniguchi, a Japanese scientist, was the first to use the term nanotechnology in 1974 and defined it as mainly consisting of the process of separation, consolidation, and deformation of materials by one atom or one molecule at a time. There was a progress in nanotechnology since the early ideas of Feynman until 1981, when physicists invented a new type of microscope at IBM Zurich Research Laboratory known as the Scanning Tunneling Microscope, STM. STM allows to measure the surface electron density and topography at the atomic scale. In 1983, the group published the first STM image of reconstructed surface of the silicon wafer, which nowadays can be routinely imaged. This was considered to be a landmark development as it demonstrated the capability to work at the atomic or nanoscale. The inventors received the Nobel Prize in Physics for their design of the STM later in 1986. A few years later, in 1990, STM was used to manipulate 35 individual xenon atoms on a nickel surface and formed the letters of IBM logo as shown here in the image. This invention led to the development of more devices of its kind, like the atomic force microscope, scanning probe microscope SPM, which is a cornerstone in nanotechnology, enabling the manipulation and characterization of nanomaterials, nanowires, nanoparticles, and nanostructures. SPM is a powerful technique used to image surfaces at nanoscale by scanning a probe over a specimen, allowing an unprecedented resolution and detailed analysis of material properties. In 1990, scientists used transmission electron microscope TEM to see and analyze the material at atomic level resolution. TEM helps reveal the structure, size, defects, and the composition of nanoparticles with unmatched clarity. Also, XRD, X-ray diffraction setup, allowed researchers to identify crystal structure of material, its phase and grain size, helping them to understand how nanoparticles are arranged in the atomic level. All these advanced tools such as SEM, TEM, XRD, and AFM have enabled the rapid growth of nanotechnology. In 1985, fullerene, a very stable form of carbon molecule C60, was discovered, expanding the understanding of carbon's structural diversity and opened new avenues for research in material science and nanotechnology. During this period, other carbon molecules of fullerene family led to the emergence of new class of carbon materials of same family with enhanced mechanical and electrical properties. They exhibited excellent electrical and heat conductivity, extraordinary tensile strength, which had potential to revolutionize various industries including electronics, structural materials, and medicine. A few years later, in 1991, Ijima et al. Observed hollow graphite tubes or carbon nanotubes by transmission electron microscope (TEM), which form another member of the fullerene family. The strength and flexibility of carbon nanotubes make them potentially useful in many nanotechnological applications. Currently, carbon nanotubes are used as composite fibers in various polymers to improve the mechanical, thermal, and electrical properties of the bulk product. They also have potential applications as field emitter, energy storage materials, catalysis, and molecular electronic components. These developments also sparked a renewed interest in carbon nanomaterials and recognized so significantly that the Nobel Prize in Chemistry in 1996 was awarded for the discovery of fullerenes. In year 2004, a new class of carbon nanomaterials called carbon dots, C dots, were discovered accidentally by Zhu et al. During the purification of single-walled carbon nanotubes. C dots with interesting properties have gradually become a rising star as a new nanocarbon member due to their benign, abundant, and inexpensive nature. In the same year, 2004, researchers isolated a single layer of carbon atoms identified as graphene at the University of Manchester. They used a simple method of peeling layers from graphite with sticky tape to extract and observe single layers of the material. After the discovery of graphene, carbon-based nanomaterials became the backbone of the almost every field of science and engineering. Graphene was isolated and identified in 2004 by researchers at the University of Manchester. They used a simple method of peeling layers from graphite with sticky tape to extract and observe single layer of material. And after the discovery of graphene in 2004, carbon-based materials became the backbone of almost every field of science and engineering. And the researchers received the Nobel Prize in Physics of year 2010 for their groundbreaking experiments regarding the two-dimensional material graphene. Carbon nanomaterials have become a fascinating class of materials now, which offers a unique combination of lightweight, high strength, and excellent electrical and thermal conductivity. These properties make them essential for advanced technologies in energy storage, electronics, and structural applications. The challenges of thought experiments thrown by Feynman inspired the development of a new scientific field. Though it took 26 years for both challenges to be met, but one of the most exciting aspects was yet to come. Feynman has a vision to build machines with dimensions on the nanometer scale, means atomic and subatomic scale. And he kept on inspiring the researchers to explore the techniques to work in this direction. The only possible way for achieving this was to control a molecule by another molecule. Chemists began designing molecules that could move or change shape in a controlled way. The major breakthrough came in 1983 when a French researcher group devised a way to take control over the molecules. And in 1999, the first molecular motor was produced. During 2000 to 2010, molecular machines became more sophisticated, advanced, and functional. In the year 2011, the research group also built a four-wheel drive nano car. The first motor wasn't exactly fast, but research group has optimized it. And in 2014, the motor rotated at the speed of 12 billion revolutions per second. They literally developed the world's smallest machine, a tiny lift, artificial muscles, and minuscule motors. They have developed molecules with controllable movements which can perform a task when energy is added. By the development of computing power, it demonstrated how the miniaturization of technology can lead to a revolution. The Nobel Prize in Chemistry in the year 2016 was awarded for the design and synthesis of molecular machines. Nanotechnology has huge potential to play important role in the various fields of science and technology. The progress of nanoscience and technology in different fields of science has expanded in different directions, have become of fundamental importance to wide range of real life and engineering applications. It has made possible many advances in smartphone technology and other modern electronic devices for daily uses. The development of any new science or technology holds both promises and risks for society. It is up to the society, including citizens, scientists, governments, and businesses, to agree on the best way to develop such technologies while minimizing the risk to both us and the environment. The history of nanotechnology shows how curiosity-driven science evolves into a transformative technology that now shapes every modern industry. From early theoretical ideas to today's advanced nanoscale tools, the journey of nanotechnology highlights humanity's continuous push to see deeper and build smaller. Its history is a foundation and an inspiration for the innovations yet to come. Now, hold your breath and get ready to explore the amazing world of nanotechnology. And these are the references for further reading. In future lectures, now we will go deeper into the field of nanotechnology. Till then, brush up the knowledge given up to you up to this lecture. Thank you for watching. And those who are curious about knowing the latest developments in the field of technology may catch me up on my YouTube channel PHYSIFER and get new information and some interesting technical facts unveiled in it. Thank you for watching.